Yeah, any questions? They're straightforward. The only thing you had to do with those was pick the curl. Anybody else? Okay, good. Well, there's two things that I'm going to do this one. I think it's most, it makes the most sense to do it. I'm going to talk about magnetic forces first before I talk about magnetic flux and flux, integrating the magnetic flux density to get the total magnetic flux. And I think it'll make sense. So this is magnetic forces. Or magnetic force. What I want to do, I'm not going to start with permanent magnets. I'm going to start with just currents creating B fields and the actual force created from a B field on a differential current element. So if you have a differential current element, I, dl, as such, then there's a B field not created by that current, right there. Then there's a magnetic force on this current element, IDL, that's equal to IDL cross B. Now that's sort of a statement of fact. It's based on experimental observation. So the B field, remember, is equal to mu H. And here, mu is equal to mu 0 times mu relative. And mu 0 is 4 pi times 10 to the minus 7th henries per meter. It's a constant, right? Just like epsilon. Now, do you remember what we term mu? There's a word for it. Like epsilon was the permittivity, sigma was the conductivity. What is mu? Permeability. Permeability, magnetic permeability. So here, the B field actually is not in terms of mu H, it's just given as B. Now there's a couple of important things you have to understand about this. Whenever there's a cross product involved, if the B, it causes anything, two vectors that are in the same direction, if you cross them, you get 0. Do you all follow me on that? So if you had a differential current element here, and you had a B field everywhere in that direction, the net force caused by that B field is 0. Do you all follow me on that, everyone? It's important to understand that. The maximum force would be felt when the B field itself was perpendicular. If you had a B field like this, now just think about that. If IDL is that way and the B field's that way, which way is the force? Take a moment and think about it. And I suggest you use your right hand.
Out of the board?
Whoever said that, it's out of the board, right? Take your right hand, use your index finger, put it in the direction IDL. This is the standard right hand rule. Then cross it into the second vector, B. The resultant, your thumb points in the direction of the force. Y'all with me in that class? That's just fact. So that's how you determine the force. Now, there's quite a few things I'm going to say about this, but I want to go through some classic problems, force problems. Does everybody follow me when I said the right hand rule for that? Follow me? Okay? All right. And I got a story that has to do with the first one of the early nuclear weapons tests related to this, that my major professor, when I was in college, finished my PhD, he happened to be involved with some of this stuff. And I'll get to it in a second. Believe me, it's interesting the amount of force you can get. So let's say we have two wires. We're going to have a current I going that way, and we might as well make the same current I going this way. They're infinitely long straight wires. Kind of remind you of really power lines. We're going to separate this by a distance d. Just straight lines. I'm not putting any coordinate systems on here for a reason. They're parallel to each other. Now, if you think about just the magnetic field caused by this, I'll call this the first current source and this the second. Well, you know that the way I like to think about this, you know, the H field in general from any infinitely long current is really I over 2 pi rho, where rho would be the radial distance, and it would be circulating in the a phi direction. Do you all follow me on that? So if I come a distance rho out from the board, I'll get a magnetic field. That will be the magnitude I over 2 pi rho, or the distance at this point. It'll be circulating this way. Do y'all follow me? Now, as I move around, my index finger is I'm trying to show you the direction of the H field. The H field at this point, or in this plane where this current is, would be into the board. Do y'all follow? How many see that right there? That means if you took a look at this, the actual B field created by the first current here would be equal to mu 0, if it's in free space, times I over 2 pi. Now I'm going to have to put a coordinate system on here. So I'm going to call this the origin. I'll call this x, this direction y, and straight up z. Do you all follow me? So this is the origin. I'm going to have to do this to get the next part. So when I look at this, do you all agree that the B field caused by the first current source that's going up and down on the z-axis here, it would be magnitude-wise mu 0 I over 2 pi, but it would be going into the board. You all see that? How many see that? You all follow me back there, guys? You see it? Or not? Remember, magnitude first, I over 2 pi rho. Rho in this case would be d, wouldn't it, class? That would be the separation distance, correct? What's the direction into the board the way I've drawn it? If x is coming out of the board, what's going in? Minus ax, right. So it'd be in the minus ax direction. Okay, that's the B field. Let's find what the force is per unit meter on this. So I know now, I'm just going to say I have my I, that's still I. dl would be actually dz az. That would be my IDL. I didn't put it here, but I'll put it. The differential force is equal to IDL cross B. This B field is not created by the current here. It's created by some external point. Y'all with me, everyone? So when we take a look at this, that would be, this is my, I'm getting the differential force here on this current right here, this current element. So it's I dz az, this would be dl. Do y'all follow me? You have to have not only differential length, dz, it has to have a directional sense. Do y'all with me? The dz, az is the direction, it's going straight up. Crossed into B. This is the B field, so it's crossed into mu 0 I over 2 pi d, and it's in the minus ax direction. Now take a look at that and realize I've just applied this law to this situation. Do y'all agree? How many see that right there? All right. Now, take a look at what happens here. That means the differential force, I'm going to do the cross product in a second. You see how I have an I squared? Y'all follow me? I have I times I squared. I have mu 0, I squared, over 2 pi d. And then I have az crossed minus ax. What is az crossed into ax? Just think about it. Az crossed ax is ay, correct, class? With a minus sign, it's minus ay. Now, I want to show you why I said that. And the units of this would be newtons per meter. Force is in newtons. We do it. So that's the differential force, and the force per meter would just be this times 1. Wouldn't it, class? 1 meter, because it doesn't change over length. Follow me? Which is important to see. Now, I want you to see one thing about how you get force using the right-hand rule, and then I'm going to say some general truths. Remember, it's always, I want to look at the direction of the force here. IDL is in that direction, right? Cross B, IDL is in this direction. Cross B goes into the board. the force is that way. Can you all follow me? That's minus y, isn't it, class? Take a good look. Right? IDL's up, right? That's AZ, correct? Crossed in the B field. B field's going into the board, it's minus AX, right? Your thumb points in this direction, I'm saying y is that way, that's minus y. Do you all follow me? So the wire's being pulled this way, you might say. Do you agree? All right, now go over here to the same, you might say the mirror problem. I have IDL in this direction. Which direction is the B field from that current here? Just use your right hand. Some people do it this way. They say, put your thumb in the direction of current, and on your right hand, your fingers will swirl in the direction of the H or B field, if it's an infinitely long thing. So just do it. If I put my thumb in that direction, you see it would be coming out of the board here. Everybody? So now if I look at the differential force here, I have IDL going up, cross B coming up, my thumb's pointing that way. Y'all follow me? Same magnitude of force, only opposite direction. These guys are pulling together. Do you all follow? Now the force per meter that you would get, here's where it gets interesting for me personally. If we talk about the force per meter, we would integrate this over a meter, right? And you'll notice this whole thing is a constant versus dz, so it's just multiplied by a meter. Therefore, the force per meter attracting these things would be equal to mu I squared over 2 pi d, and that's just the magnitude of the force per meter. It's proportional to I squared, inversely proportional to the distance separated. Now here's the story. And by the way, I can't prove this is true, but I've talked to my friend at MIT named Earl Williams. We've done lightning research together. He's an electrical engineering professor. Phil Reppert is another friend of mine. I've talked to quite a few people about this. It is true and accepted, but finding information about it, good luck. Do you know what the Bikini Island experiments were? Nuclear weapon experiment? All right, try to find some real information about that. You can't. It's happened, it was documented, and a lot of things came out of that about hardening for nuclear weapon events, but nevertheless, you can't find any real information that I know, unless there's something out there I don't. So here's what happened. Long ago, out west, they blew up some small atomic devices. They're 100 kiloton, 50 kiloton kind of things. And the first one, there were two tests out there that are really famous. But anyway, they're in the middle of nowhere. There's nothing out there except one thing. There was a thing called a gold rush, and mining was all over the place. And railroad tracks were used as the primary mode to move large, heavy objects back and forth. Well, they get buried. Do you know this story?
No, I'm just thinking about it.
All right. Well, they get buried. There's also railroad tracks that go into tunnels for silver mines and stuff. Anyway, there's tons of railroad tracks that are not visible on the surface. They're buried 8, 10 feet under from debris, sediment, all that stuff. They're somewhere under there. So the first nuclear weapon goes off, and I did a paper on this event, basically. What happens is you get a very large positive fireball left, a positive charge, and all the electrons, called Compton electrons, get scattered all over the world, you might say. They get into the ionosphere. But when that happens, they want to get back to their parent charges. They want to get back to that positive center. So they return through the path of least resistance. And you know what doesn't have a lot of resistance? Railroad tracks. They're metal. And so this thing went off, and apparently, wherever it went off, the railroad tracks had a component in the direction of the radius to the actual bomb's explosion. Now, if they ran parallel to it, there would be no induced currents, but they're running like this. So some of this Compton electron flux that's scattered all over the Earth, it's coming down that railroad tracks. There's zero resistance path to them, you might say. It's not quite true, but so they flow down there. Here's what they found. So they're looking, because they have to do an assessment of the area to see exactly what happened. They looked at, believe it or not, there was quartz all over the place because basically sand got fused into glass. It was so hot. And they found that these railroad tracks were pulled off the wooden blocks that separate them, the ties, and fused together over a fairly long portion. Now, You know how much force it takes per meter to shear a railroad track off? Any idea? 10 tons or more of force. We did this calculation. When you back it out, this current right here, that's millions of amps to do that. Now, that's actually quite reasonable, because have you ever seen any kind of just view of a nuclear weapon going off, small ones I'm talking about, and take a look at the lightning caused by it? Anybody? They have them on YouTube. You'll see unbelievable amounts of lightning that are, they call them Super Bowls. Normal lightning is about, clouded ground strikes is about, peak current 20 to 50 kiloamps, typically, short durations. There's a thing called a Super Bowl that happens. It gets up to almost 300 kiloamps peak current. The current from these things are orders of magnitude, and it's because of the amount of charge that's displaced. And most of this stuff is very classified and sensitive. And frankly, I don't have access to it. I know about it because I know people that know about it that mention it to me in a non-classified way. But I found it very interesting. Now, the second thing about this force business here is I worked on a railgun. Not a commercially available weaponized railgun. A railgun created by a bunch of seniors because they thought it was a cool thing to do, and I got permission to do it. Sure, I'll do it. But I didn't know what I was getting myself into. It was a bunch of kids that they should have been working for the Army on special weapons or something, because they got it shooting over a mile a second with pieces of Lexan, which is what hockey rinks are doing. Anybody have any idea how fast that is? Let me ask you, how fast is a 30-06 bullet? There's got to be some guys that hunt. Huh? About 3,000 feet per second, right? A mile a second is 55,280 feet per second. These guys are shooting over that with a bunch of stuff we jury-rigged over at the physics building years ago. Then it got all shut down because of 9/11. And the Department of Homeland Security didn't think this was a really good idea. But when we were doing that, we were using currents that got upwards of 400 kiloamps. Just remember that, peak current. That's a lot of current, all right, in short duration. But the thing that I noticed when we're doing that, with our current, it's differential. You see how these guys pull apart, or pull together, pardon me? Currents in the same direction, pull together. How many remember that from physics? Currents flowing in the same direction always pull together. But we had this going on. We had a whole lot of current going the other direction, and we're discharging these high energy capacitors. So my first experience was, I'm watching a couple of what I thought were very secured lines just tear themselves apart, and I'm so glad my leg wasn't around there. And I realized this is a different kind of a problem. I'm not used to this kind of a problem in electrical engineering. What I also found out was we had to use an inductor to slow the rate that these things discharge, so we had to build a special inductor. Made it out of 4-aught wire. We had to use fiberglass, this Bondo stuff that you actually, anybody ever fix a car, repair a car with Bondo or anything like that, or a fiberglass boat? And wrap layers and layers of this on this PVC core. We had 4-aught wire going around there. But the core was hollow, and naturally guys like experimenting when they have a chance. So we're going to discharge all this current from a capacitor bank through this inductor into a railgun that I'll get to later, and it'll launch these things. They don't use a small percentage of the actual available energy, but they would take empty Coke cans and stuff and throw them in the center of this hollow PVC after that current was discharged. And they found out that that was a great way to create a bazooka, because the things would crush it and fire right into the ceiling, and they thought that was great fun. Now I'm here and I'm thinking, I'm probably the target of opportunity in all this. I can see myself catching one of these things in an accidental way. But I mean, they had so much fun with that. They were trying to find things to shoot through. I don't know why this is a big deal. You can shoot through a pine board. Well, the 22 can do that. Bigger things, bigger things. We had to get deflective plates in the water for these things to stop. This was turning into, it was getting out of hand. Because they want to weaponize this thing, take it outside. Let's take it outside. Each one of these capacitors is 250 pounds. You're going to take a rack of 5 or 6 of these outside? Are you nuts? But they're convincing, oh, it's easy to play a pickup. This is not, I'm not kidding about this. If you ever find these videos, I got a whole bunch of stories about the Department of Homeland Security getting involved and becoming me and getting a hold of some really not so savory characters, but there were videos that those kids had that were better than anything you'll see on Saturday Night Live. One of them dressed up as a proctologist, did a specially designed elephant examination. They got a stuffed elephant from Walmart. I went there, they made sure it went. And if you guys can find that, you need to, because that guy, his name is Gus Lott. He should be a comedian. He was better, funnier than anybody I've ever seen. You look it up. If you can find it, let me know, because it's all been, I think it's been sanitized. I think they got that thing everywhere it was. So that's at least the reason to be interested in magnetic forces. Now, that's the standard magnetic force. Do you remember that from physics, that problem I just did? How many do? It's classic. A couple other things we'll talk about with magnetic forces, and I'll do the loops and stuff in a bit. But you know, it's not just a current element. If you have charges, and this is a classic, if you just have a charge Q, and it's moving with a velocity v, and there's some B field. Now I'm assuming this B field is constant everywhere, and it's well defined, well known. Well, there's going to be a force on this. There's going to be a differential force on this charge caused by the motion. And this is magnetic force, and it's called the Lorentz force, I think sometimes. It's called a couple of things. But the actual force on that charge is equal to QV across B. Q would be the amount of charge, V is the velocity in meters per second, and B would be the magnetic field. Y'all follow me? It would be, the magnetic field is in either Tesla or Webers per meter squared. Now if you look at this, it's important you at least appreciate what's going on. If you have something, if you have a charge, say I'm going to put the B field, I'm going to have the B field everywhere coming out of the board. And then I'm going to go right here and I'm going to have my charge QV. And I want you to tell me which way the force is. Remember, this B field is out of the board. So just think about it. I got QV in that direction, cross B. Which way is the force? Y'all see it's downward, class? Use your right hand, make sure. How many can see this? I want to make sure you do, because if you don't, I need to help you now before you get yourself in real trouble. So there's going to be a force pulling it downward, right? Now, that force will cause the trajectory to be altered. It will do this. Y'all follow me in this class? Now, at this point, when it's moving straight down, let's just take it a step further. Now I have my QV going straight down. Still the B field is out of the board. Which way is the force? QV, right? Cross B, here's where you look like idiots, right? Got your elbow up there and you're doing it. I see this in class when I'm giving an exam, I can tell what they're doing. It's going this way, right? Correct, class? Let's keep going. And that force would deflect it this way. Y'all follow me? So now it's going to come down to here, right? Let's say it's going down here. I'm moving about a quarter of a circle each time. QV cross B. Now it's going this way. Which way is the force? QV cross B up, right? And it will continue, and it will make a loop. This is called magnetic bottling. Now you've probably heard of this in physics. This is the mechanism. The best way to think of this as an analog to this is just take, I don't know, take a lead sinker at the end of some fishing line and swing it around your head. All right? It can't move at a greater or lesser radius because that fishing line is holding it. And the acceleration inward is the same thing as v squared over r, which would be the acceleration outward, if you remember from physics, right? It's exactly that, so it moves in a constant circle of constant energy, unless I'm really doing something accelerated. So there's no energy being gained by this thing when it's moving. It'll always have the same velocity in terms of its magnitude. Its path will just be bottled up. It's called a magnetic bottle. Now, the larger the magnetic field, the smaller the radius of this magnetic bottle, and I'll show you that in a second. I want you to just appreciate the physics. So where do you see magnetic bottling all the time? Where it happens is when you get solar radiation that's charged particles, primarily positive charges, it can be electrons too. When they come into the poles at high altitudes, there's very little collisions. So you get these remember the magnetic fields of the Earth, they kind of do this kind of a deal. When the charges are coming down, what they end up doing is getting caught in a magnetic bottle. And the closer they get to the Earth's surface, the tighter that magnetic bottle gets, so they spin at a higher frequency. And it's called a whistler. Has anybody heard that term, whistler? Well, some of you will definitely hear about this. And I remember this professor I had a ham radio shack. And at one time before the internet, the way you communicate with people all over the world was with ham radio. If they're in the Ukraine or in China or anywhere in the world, you could do it, and it was usually with Morse. They did have voice and stuff like this. But I remember being up there one time, so he tunes it, and I'd start hearing this. He goes, do you know what that is? I don't know. Those are whistlers. And he explained to me that there was an event, a solar event, and what we were listening to was actually it was the radiation from this magnetic bottle that was getting into I think it was the 10-meter band, but I don't remember exactly. It's kind of interesting to me. That's the reason for it. So anyway, getting back to this problem, here's something you should be aware of, because some of you are going to have to know how to do these things. You'll be dealing with stuff that has to do with satellite technologies, and this is something you have to be aware of and know how to do. If you're talking about magnetic bottling, the force, the magnetic force there would be this. So this would be, I'll call it just magnetic force, right? Now, I told you that anytime you have something and it's moving at a constant radial distance and a velocity, constant velocity, there's an acceleration on the string. If you remember the old classic problem where you had a stone, it's moving at a distance d, and it's got a linear velocity v, but there's an acceleration here internal, and that's v squared over d, or the radius r. How many remember that? That was the acceleration due to the motion, right? Because it's confined. You all with me on that? If there was no acceleration, we just keep going in a straight line. The acceleration doesn't change the actual velocity's magnitude, just the direction. Y'all follow me? Y'all remember that problem in physics? It's one of the most classic problems. So what they normally do is this. For that particular case right there, the magnetic force in magnitude is QVB. That's just the magnitude of the magnetic force caused by the bottling effect. All right? They set that equal right there to the actual acceleration in mass, because this thing would like to keep going straight, right? As a matter of fact, if you cut the thing anywhere, that thing will just keep going straight, or it's a perceived outward acceleration, actually. So when you take a look at this, this is going to be equal to the acceleration due to the motion itself, which was v squared over, in this case, I'll call this r from the center here, because that's the classic way of doing it. V squared, maybe I better use D. My R looks too much like my V. So it'd be V squared over D, and then it's times the mass of the actual object. So this thing has charge Q and mass M, and that would be the mass would be in kilograms, by the way. So when you take a look at this, that equation holds true, absolutely. You're balancing the acceleration or I mean, basically the outward acceleration is offset by the inward acceleration. The thing is just moving in a closed circle. Then what happens is, if you look at this equation, I'm going to solve for just the radius d. If you look at this, I get d is equal to v squared m divided by q, v b. I'll cancel the v's, so now I get v times m over q, and then divided by the b field, 1 over the magnitude of the b field. And that is the distance d, or the radius. I'll just call it radius. Right here. Q, mass over charge, 1 over b. Why am I saying this? Because there's something very important we use this principle for. Do you know what mass spectroscopy is? How many have heard that term? A mass spectrometer is a very, very low pressure unit that injects charge, maybe injects something of unknown value, but they know the charge on it. And what happens is these things will spiral at a given radius that has to do with the B field and the ratio of mass to charge, and they'll put radial filters out at a certain distance. And when those particles, obviously the ones that are moving in the orbit at that given radius that's being collected, that's the ratio of charge to mass for a given B field. So they can figure out what's in. There's certain very well known charge to mass ratios for most of the common aerosol particles and things like this, and they can easily figure out, just taking a sample, if they're in this room, if they run it through a mass spec, they know the percentages of all the gases here. They'll ionize them, they'll figure it out. Have you ever dealt with physics of mass spec anywhere in your classes? Where'd you get it?
Physics class.
Basic physics?
Physics too, yeah.
All right. But that's the principle that governs mass specs. Now, I'll tell you, you can see the more mass, the larger the radius. Makes sense. The heavier something is, the less the magnetic field can actually affect its trajectory. The larger the B field, the smaller the radius. And it's proportional to the velocity right there of the charge. So this is a kind of a standard, I'm trying to think of the word for this, but this is one of the most classic physics examples of a use of any kind of magnetic bottling. It's used everywhere. Just be aware of that, okay? And if you're thinking, well, what kind of a problem could I ask? Well, I could say for a given mass, charge, velocity, and say radius, what B field would cause it. So it's basically, with this equation, if you know all of the components but one in it, all of the actual values, you can get the other. I'm not going to ask anything tricky about this ever, but I want you to make sure you can at least appreciate what's going on and the forces for both current and on just the charge moving. Now, something else about this, I should say, that everything I'm talking about is very general and assuming there's no collisions. In the real world, even at low pressure, there's a certain finite number of collisions. And whenever the number of collisions becomes like more than one for a single orbit, then you get collision-dominated effects and things change rapidly. And I could spend more time on this, but right now, I think, for now, just appreciate why things like mass specs and whistlers and really why wires pull together because of magnetic forces. Now that's really just charge, current, and we can then we can do loops too, because that's another magnetic force problem. That's classic. Next time. Actually, I'll do that next time. So, what I'm gonna do next time is gonna be some of the physics, the torque of like a loop, and I'll also talk about bar magnets next time. I'll give you a heads up what I'm up to. But now, did I talk about magnetic boundary conditions in here? I thought I did. No? Pardon?
Not yet.
All right. When we talk about, I mean, you remember when we talked about the electric boundary conditions, it was E tan 1 is E tan 2, and D normal 1 was D normal 2 if there was no surface charge density. Do you all remember that? Well, with magnetics, if you have a surface here, I don't want to do it the way he does it. This is on page 259. If you have region 1, region 2, and try to assume this is an infinitely long planar situation. You've got two different materials. And we're going to have two different H fields. We're going to have an H above, call it H1 or B1, and we're going to have an H2 down here. And we want to know how H1 is related to H2. There's really two things that happen. The first is the tangent fields. H tan in region 1 is equal to H tan in region 2. That's true generally. I'll prove that. And the second thing is B normal in region 1 is B normal in region 2. Now this one, star it, and this is assuming the surface current densities equals 0, or if K is surface current density is 0. I'll get to the one where how you have to modify that. And here's how they usually prove this. And it's the standard way. Remember that H field up here is going to be the same everywhere above there, because we're looking at a very small region where there's no noticeable change in the H1 or in H2. Can you all imagine that? So what they'll do is this. They'll start by saying, and you don't have to write this down, it's in your book, they'll have a little pill box of height H, and I know that there's going to be some tangent component up here of H1. Well, actually, I'm going to go on this one. This is going to be the tangent component, though. And there'll be a component here. Now, you don't have to worry about the direction here, but this is going to be the orientation and integration. And I know that the integral of H dot dl around a closed loop is the I penetrating that loop or enclosed by the loop. Now, here's the deal with this one. What they usually do is take the limit as H is approaching 0 of this integral of H dot dl for this situation I've shown you. And by the way, this thing's symmetric. The same amount is above as below this boundary. And we're going to let this H value collapse down to 0. Then when we do the integral of H dot dl around here, I'm going to assume there's no surface current density where this problem needs to be changed. But then what we do is find that we have H tangent in region 1 times, call this length L here, times L, and it's minus H tangent in region 2 times L. The reason it's minus is, in a path integration like this, you pick a point and you integrate. Here, the differential length is in the negative direction. Here, it's in the positive. So it'll be positive and then negative there for the net integration effects. Do y'all understand what I'm saying here? You don't have to make this thing into a very hard mathematical problem. But realize when you're doing a path integration, if these two were the same, I would get 0 around a path integral. If if I start here and go around, the same amount I gain here, I'm gonna lose here, if that makes sense to you. And what this really means, if that's 0, it means the tangent field, H tan in region 1 is H tan in region 2. And that's true always if the surface current density is 0. Now, if it's not 0, if I put a surface current density in there, then the easiest way to get it is H tan 1, where you take H tan 1, or the tangent field in region 1, minus the tangent field in region 2, and that will be the surface current density K. I'll talk more about that with some examples in a bit, but this is like, that will work for surface current densities. Normally, H tan 1 is H tan 2, almost always. Now for the B field, yeah.
What'd you say that was again?
That's K is surface current density.
Surface current density, okay. Thanks.
And it's in amps per meter, and it is a vector. Which means this should be a magnitude then. Now, I'll tell you one other thing, when you do this, a lot of times after you do a few problems, it becomes real clear. But until you do a few problems with this stuff, you're still got some concerns about your interpretation of what I say. So I'll give you some problems, we'll go over them, and I'll try to make it as clear as possible. The B normal 1 equals B normal 2. Well, the way they come up with that is, think of a small, think of, like these tobacco things, Copenhagen and stuff, they come in these little tins. Think of something shaped like that, very short cylinder of height h. Now, if you take, and this is a fact that I mentioned, do you remember me mentioning divergence of the B field is 0? How many remember that? What does that imply, anybody? One thing, it says no magnetic monopoles. There is no singular magnetic positive charge or negative charge. They have to be in a dipole. That is the differential form. But this means the integral of B dot ds over any closed surface is also 0. So before, when you had the integral of D dot ds over a closed surface, it was equated to all the charge inside that surface. Since there is no magnetic charge, the integral of B dot ds is 0. Do y'all follow? Now, what they'll do here is say, if I take the limit in this situation, here's B normal in region 1, and here's B normal in region 2. If I take and look at the integral in the limit as h goes to 0 of the integral of B dot ds, what I really find is B normal in region 1 times the area of the top in region 1, that plus B normal in region 2 times the area, or minus that actually, minus that, is equal to 0. Let me explain what I'm doing here without spending a lot of time getting into the mathematical weeds. If I look at this, the top one here has an area A and it's pointing in this direction. Do y'all follow me on that? It would have some magnitude A, the differential surfaces in that direction. Y'all follow me? So when you dot it into the B field, you're going to get some positive sense that the B field's up. I have the B field going in that direction. Here, the differential surface is in that direction, right? And the total surface, magnetic vector surface, or sorry, the surface area vector would be down, which would be negative. These two would have a negative sense. And when you integrate this over that, it would give a minus there. Just realize that this thing has to do with the orientation of the surfaces. One's positive, you'll look up, one's negative. You do this, if it's equal to 0, you can forget A, and what it implies is the normal in region 1 is equal to the normal in region 2. And that doesn't matter if there's a surface current or not. That's always true, always true. So those are the boundary conditions that occur at boundaries where there's different magnetic materials. one really important, well, there's a couple takeaways from this. Now, write this down. This one's doesn't come out in the reading in the book, but it's important. If you have an infinite, say you have a ground plane, a piece of metal that's thick, it's not thin. In other words, a metal ground. And you have a surface current K on it. This would be the surface current density. This is the planar region. And this is surface current density. Then the H field associated with this is simply going to be equal to do this the way he he's going to do it. He'll have K crossed into N, where N here would be a surface normal. Let me explain this in a little easier way. Please remember this. This is going to be a plane, say it's a very good conducting surface, just a metal countertop or something like that. It's got a surface current K. Say it's flowing into the board. With me? All right. That would be in amps per meter. You want to know the direction of the H field just above this surface? Take your right hand, take your thumb, point it in the direction of K, and your fingers curl in the direction of the H field. Now, can you all see that if it's going into the board, the H field is that way? Y'all with me? And it is always perpendicular to K, and it's also perpendicular to the normal to the point. So if I've got K going there, the normal would be upward. And if you look at this K dot normal, it's that way. Can you all see it's that way, class? Now, the reason it's only one component, we don't have H tan 1 minus H tan or 2 or anything like that, and I just have K vector cross normal because the H field down here is 0. It's a good conductor. Y'all follow me? If you have just a conductor below there, the H field 0. Not a thin sheet, I'm talking about a conducting surface where there's nothing below there that can have sustain an H field. And this is real important to know. And the reason is most of the time when they measure surface currents induced on any kind of like say a tank surface, if it's metal, they don't measure the current with any kind of a current probe. What they do is they'll have magnetic field probes that take a look at the rate of change in the magnetic field. They're called B-dot probes, and they'll use that. I'll talk more about that later. But as electrical engineers, you should be aware of that when you measure surface current densities, it's with B-dot probes. And they're used all the time when you do, a lot of you people be working in Huntsville on radars or things related to, I guess, MISIC and things like that, where you're going to be dealing with surface current measurements. My first real experience was back in 1990 when we did the hardening of or liking assessment of the multiple launch rockets right before the Gulf War. We had to use these B-dot probes, and I got real familiar with them. All right, I'll put some homework up on Friday. You're wondering about the quiz. It'll be related to the homework due today and the current homework I'm going to give you. And it'll be straightforward. Come on.